Good morning, students. We are going to start an experiment called Hall effect. When a current carrying semiconductor is placed in a transverse magnetic field, it develops a potential difference or the voltage which is called Hall voltage. The direction of the Hall voltage is perpendicular to the direction of the current and the direction of the magnetic field. So here is the schematic of the experimental setup. This is the semiconductor specimen, and this is the direction of the magnetic field BZ, and this is the direction of the current through the sample, and this is the direction of the Hall voltage or the Hall field, which is perpendicular to the BZ and IX. So these are the electromagnets, and we can understand the direction using the Fleming left hand thumb rule. This is the direction of the magnetic field, this is the direction of the current, and this is the direction of the force due to magnetic field. When a charge carrier passes through a magnetic field, it experiences a force which is given by V cross B. Here the angle theta is 90 degree, so therefore this is the expression for the force due to magnetic field BZ Q into V. So because of this force, the charge carriers will be pushed apart. The electrons will be pushed to the one side and the holes will be pushed to the opposite side. So because of this, there is a field which develops, and it is given by Q into EY. So at equilibrium, we have a situation where the force due to electric field is balanced by the force due to the magnetic field on the charge. So Q into EY equal to Q into BZ into Vx. So now by substituting, we get expression Vx is equal to Vh divided by W into Bz. Vh is the Hall voltage. So we have written the field as a potential gradient, Vh divided by W. So now we substitute for Vx, which is the drift velocity in terms of the current density. J is equal to Ne into V, where J is the current density, which is given by Ix by W into T. Current density is the current divided by the cross-sectional area. So cross-sectional area is W into T of the semiconductor, and Ix is the current passed through the sample. So by substituting that, we get Vx is equal to Jx divided by N into V. So substituting for the drift velocity, we get the expression for Hall voltage, which is given by Vh is equal to Ix Bz divided by N into T. So here Vh is the Hall voltage in millivolts, Bz is the magnetic field in Tesla, N is the carrier concentration per meter cube, T is the thickness of the semiconductor sample in meter, and Ix is the current through the sample. So here we pass a current of 50 milliamps, and the thickness is also given, and we need to find out the carrier concentration N. The application of the Hall effect is we can find out the type of the semiconductor, whether it is N type or P type. We can find out the majority carrier concentration, whether the electrons or holes. We can find out the carrier concentration per meter cube. We can find the mobility of the carriers, and this experiment can also be used as a magnetic sensor. Because of the magnetic field, we develop a Hall voltage. So if we know the Hall voltage, we can do the reverse calculation and find out the magnetic field. So this can be used as a magnetic sensor to find the magnitude of very weak magnetic fields. So here we have the data set. The experiment is explained in the another video, where we have changed the magnetic field and we have noted down the Hall voltage. So in the experiment, we have not really changing the values of the magnetic field, but we are changing the current through the electromagnet. And this is the calibration chart. If we pass a current of 200 milliamps through the electromagnet, it gives a magnetic field of 0.07 Tesla. So we vary the current in a step of 50 milliamps, 200, 250, 300, 350 up to 500 milliamps, and the corresponding magnetic field is given in the calibration chart. So it varies from 0.07 till 0.175 Tesla. And correspondingly, for each value of magnetic field, we have to note down the Hall voltage. So for initial value of current of 200 milliamps, we got a Hall voltage of 3.94 millivolts. The Hall voltage is in the millivolt. So then we set the current, magnet current at 250, which corresponds to magnetic field of 0.85, and the corresponding Hall voltage which we measured is 4.94. So for 300 milliamps, the Hall voltage is 6.03 millivolts. So likewise we continue till 500 milliamps of the current, which corresponds to magnetic field of 0.175 Tesla, and the corresponding Hall voltage is 9.95. So these are the readings corresponding to the trial 1 for magnetic field of 0.07 to 0.175. So we have to note down the second trial, but before taking the readings of second trial, we have to switch off the instrument and wait for 15 minutes for the capacitor to discharge. So after 15 minutes only, we can switch on the instrument and note down the readings for the second trial. The second trial, I have taken the readings for 200 milliamps current through the magnet. We got the Hall voltage of 3.85, next 4.82 corresponding to 250, then corresponding to 300, 5.95. Likewise, for 500 milliamps current, we got the Hall voltage of 9.82. So what we do is now we take the average of these two readings, trial 1 and trial 2, add and divide by 2, we get the average. So we use the average reading for plotting the graph. So in this experiment, we need to plot a graph of Hall voltage versus magnetic field. So Hall voltage is in millivolts, magnetic field is in Tesla given here. These are the values. And we plot a linear graph. The Hall voltage varies linearly with the magnetic field. And we need to find out the slope of this graph, delta VH by delta M. So now what we do is we substitute that value of slope in the expression for carrier concentration. So we in the previous slide, we have seen the expression for Hall voltage. So here it is rewritten in terms of the carrier concentration, and there is an additional factor 3 pi by 8, so which is a correction factor for screening effect. So the remaining terms are as it is. B is the magnetic field, I is the current divided by ET into VH. So for B by VH, we are substituting in terms of slope of the graph. And while making the calculation, so we substitute the value of the current I is equal to 60 milliamps. The thickness of the semiconductor given germanium semiconductor is 1.24 into 10 to minus 4 meter. So using this formula, so we need to find out the carrier concentration in terms of centimeter per centimeter cube, centimeter minus 3. So it is typically of the order of 10 to power 22 per centimeter cube. So that is the kind of carrier concentration in the semiconductor. So this experiment is very useful to find out whether the semiconductor is N type or P type. We can also find out the carrier concentration, so required for a specific devices. We can find out the mobility. We can also use this experiment as a magnetic sensor. So this is all about the Hall effect. You can go through the next video to see how to really perform the experiment. Thank you very much. This is the Hall experiment. So we are going to perform this experiment. The aim of the experiment is to find the charge carrier concentration of the given semiconductor. In this case, it is germanium. The current carrying semiconductor, when placed in a transverse magnetic field, we know that there is a Hall voltage develops in a direction perpendicular to the direction of the magnetic field as well as to the direction of the current. This is called Hall voltage. This experiment is important. It has application in various semiconductor products and industry. The apparatus includes the semiconductor specimen. This is the semiconductor specimen, gallium arsenide. it is also called as probe, and we are going to pass a current of 60 milliamps through this. And there are electromagnets. These are the electromagnets. So we don't directly measure the magnetic field here, but we vary the current and we calibrate the magnetic field. There is a table, calibration table given, which gives the magnetic field for the given current. So this is how we change the magnetic field. And we pass a current here of 60 milliamps through the sample. So we measure the Hall voltage here, and we measure the magnetic field here by passing the appropriate current of, let us say, 100 milliamps, 200 milliamps, 300 milliamps, up to 500 milliamps. We measure the Hall voltage, which is in the unit of millivolts. This is a voltmeter which measures the voltage in millivolts, and this is the current meter which measures the current in milliamps. We pass a current of 60 milliamps through the Hall probe. So now let us start the experiment. We have to do certain calibration before starting the experiment. First, we have to set a gap of 1 centimeter between the pole pieces of magnet. So these are the electromagnet coil, and these are the poles. We have to set a distance of 1 centimeter. So that is how we apply the magnetic field. If the distance increases, then the magnetic field will reduce, which is acting on the sample. And here, for zero current through the magnet, so we have to initially set the current through the magnet as 0, and the corresponding Hall voltage should also be 0. So this is the calibration, initial calibration. All the current meter as well as the voltmeter should reduce to 0, should read the reading 0. And we have to pass a current of 60 milliamp through the probe. So 60 milliamp, the middle one, this is the current through the probe. We will set it at 60 milliamp. So now we will start the experiment. So what we do is, we will vary the current through the electromagnet and set the magnetic field and measure the corresponding Hall voltage. The aim of the experiment is to plot a graph of Hall voltage versus magnetic field. So we have to change the magnetic field, and correspondingly we have to note down the Hall voltage. First, we will set a magnetic field of 0.70, which corresponds to 200 milliamps. So we set the current of 200 milliamps through the electromagnet, which corresponds to a magnetic field of 0.07 Tesla. So that is the calibration chart. We are going to give the calibration chart for all the values of the current. And we can see the Hall voltage is 3.90. We can take 3.92. There is a slight fluctuation. So now we will increase the current to 250 milliamps through the magnet, and this current corresponds to a magnetic field of 0.085 Tesla. The corresponding Hall voltage is 4.94. So similarly, we increase the current through the magnet at a step of 50 milliamps. So we started from 200, now it is 250, then we move on 300, 350, 400, 450, up to 500. Let me just take a couple of more readings. Let us say for 400 milliamps. Let's say for 400 milliamps, the corresponding magnetic field is given by 7.94. 7.94 is the Hall voltage. Okay. So I am going to give the full chart of readings, which you plot a graph of Hall voltage versus magnetic field. So we would like to find out the slope of that, and then we substitute it in the formula, and then we can find out the carrier concentration of the given semiconductor. So this experiment is very useful in semiconductor industry. So this also has applications in magnetic sensors. So here we vary the magnetic field and we find out the Hall voltage. So therefore, if we know the Hall voltage, we can calculate the magnetic field in the backward direction. So therefore, this experiment can also be used as a magnetic sensor to determine the very small values of magnetic field. So however, here our aim is to find out the charge carrier concentration of the given semiconductor, and so I'm going to give you the readings. You will plot the readings. You will plot the readings in a graph, and then you evaluate the slope of the graph, and then make the full calculation to find out the carrier concentration. So with this, we come to an end of this experiment, Hall effect. So thank you very much.